I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on gravity and centripetal force and how we can derive expressions for orbital motion. So we're going to talk about gravity and centripetal force and how the gravitational force helps with orbital motion. So first off, we're going to look at satellites. So what is a satellite? Well, a satellite just orbits the Earth. An actual satellite or a moon or a space station are all considered satellites. And a satellite just is moving and it's falling into the Earth, but it doesn't actually fall to the Earth because the motion of it keeps it in orbit. So if we look at a motion map for a satellite, it looks no different than the motion maps we saw in the previous video, where you have an acceleration pointing towards the center, you have a velocity drawn tangent to that circular path, and all the velocity vectors are equal because they have the same altitude, it has to have the same speed. You can see that the net force, which would be gravity, also points towards the center. Now this is no different from an elliptical orbit, except the net force and acceleration still point towards the center, but you notice that the velocity, when closer, is faster, and when further away is slower. So to stay in orbit, you don't have to move as fast the further you are away. The closer you are, the object has to move much, much faster. So you can see that on the right side of the diagram. So orbital motion. When we're talking about orbital motion, we're going to use centripetal force, and we're going to set that equal to the gravitational force. Now, since we're not near the surface of the Earth, we can't just use mg. We have to use the universal law of gravity in our equation. So Fg is going to equal g times mass of the satellite times mass of the Earth divided by the radius squared, and that's going to equal centripetal force, which is the mass of the satellite divided times v squared divided by r. Now, the mass of the satellite is going to cancel out. So if you're asked a question about an object in orbit and the mass changes, how does this affect anything in the orbit? Nothing. It doesn't affect anything because the mass cancels out in our equation. So it does not affect orbital motion at all. Now, if you want to derive an expression for the orbital velocity, we start with the same equation. We know the masses cancel out, but we also have something else that cancels out. We have the radius that cancels out. So r squared, one of those cancels out with the r. So we can clean up that equation and simplify it to g times mass of the Earth divided by radius, and that equals v squared. So to solve for v, we just have to take the square root of each side. And the orbital velocity, as you can see, is dependent solely on the radius of the orbit. The radius would be the radius of the Earth plus the altitude above the surface of the Earth. So that's what the r value is the altitude, which is the height above the surface, plus the radius of the Earth. Now, if we want to find orbital period, the period is the amount of time it takes to go around one complete path, which would be one orbit around the Earth. And we know that if the radius doesn't change, that the speed has to be constant. So if the speed is constant, we know that distance divided by time is the speed. Well, the distance we travel around the Earth is a circumference, 2 pi r, divided by the period, which is capital T, so we can substitute 2 pi r over t in for that equation, and then we can just solve this equation for t, cross multiplying, and then dividing, and we get 2 pi r times the square root of r divided by universal law of gravity times the mass of the Earth. And this is the period of an orbit. You can see that the period of the orbit only depends on the radius of the satellite, the radius of the Earth plus the altitude. And we can see that the bigger the radius, the longer the period of time that it's going to take to travel around the Earth. Now, a geosynchronous satellite is a satellite that is above the same point on the Earth. So if you're able to look up and see the satellite, every single day you looked up, that satellite would be in the exact same spot. The reason for that is that it takes 24 hours to orbit. That's what a geosynchronous satellite is. It orbits the Earth once every 24 hours. So it basically matches the orbit of the Earth. And if we wanted to find the value of that radius, we could go back to this equation And we know that the period is going to be 24 hours. We have to change that into seconds. And then we can solve for r because that's the only variable that's unknown is the period. So we know the period is 24 hours. We could solve for r, where r would be the altitude plus the radius of the Earth. So if it's asking here how far above the surface of the Earth, when we find that r value, we'd have to subtract out the value of the radius of the Earth. So this is how you can derive expressions for orbital motion using centripetal force and the universal law of gravity. I hope this was helpful, and I hope you have a great day and even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter at Cavi Coaches.